Good morning, folks. How are you today? We are into lab number 3, and our focus is going to be on cold rolling or cold working and Rockwell hardness testing. So, our objectives are we are going to study first the effect of cold rolling on tensile properties of mild steel. This is the subject we covered in the previous lab, lab number 2, that was your lab 2 assignment. And then in this week and next week, we are going to measure Rockwell hardness on 3 different specimens. In my case, for the demo, I'm going to use these cold rolled steels. Actually, they are extruded, not rolled. And then for your assignment, you're going to use these brass samples, which are really cold rolled. We have made hardness indents on these. So you're going to measure the size of hardness indents using Fiji. I'm going to show you how to do it on the demo, and then you are going to do on brass for your assignment. And after this assignment, I hope you become very familiar with ASTM standard E18, which covers Rockwell hardness testing. And of course, as usual for your assignment, you're going to evaluate your numerical results, make summary conclusions, and submit a professional report by Wednesday, March 3rd. Okay, again, I want to give you, emphasize the big picture of this course, mechanical properties. So we have done hardness testing now in both the labs. Lab 1, we did Brinell hardness testing. In Lab 2, we did Rockwell hardness testing. And we found that the indentation hardness is proportional to strength. Then we did tensile testing in lab number 2, where we focused on strength and ductility, and we found that strength varied inversely with ductility. So if we did something like in our aluminum specimens, we did precipitation hardening or precipitation strengthening, we reduce the ductility. So if we increase the strength, we reduce ductility. That is what also you saw in your lab 2 steel specimens. The T4 specimen, which was skin rolled, had lower strength, higher ductility. And if we had cold rolled it to quarter hard, increasing its strength by almost 50%, we decrease the ductility. In the next lab, lab number 4, we are going to look at impact toughness. And we are going to find that impact toughness varies inversely with strength. Now, the point I'm making here is I'm trying to relate hardness to all these properties. So hardness is proportional to strength, hardness is inversely proportional to ductility, and hardness is inversely proportional to impact toughness. Since hardness is such easy thing to measure, it is such a quick test, it's a very good way of detecting changes in strength, ductility, and impact toughness. So in lab number 2, we looked at tensile testing. And this is a schematic of a metal tensile curve. So what we found is as we increase the stress, the material elastically deformed, elastic deformation only. And this portion of the curve was essentially linear, not necessarily perfectly linear, but it could be characterized by the slope, which was called elastic modulus. So this was our one major mechanical property of the material. And then we saw uniform plastic deformation begin, along with continuing elastic deformation. And it begins at yield strength. This is when dislocations begin to move and multiply, and the deformation, part of the deformation is irreversible. So this is another material property. And then we reach the maximum stress when non-uniform plastic deformation begins. we still have continuing elastic deformation. And this maximum stress point is called tensile strength of the material. So this is the third important mechanical property. And then eventually material fails and it has experienced a maximum deformation, which is percentage elongation to failure, also a measure of ductility. So these are the four major mechanical properties: elastic modulus, yield strength, tensile strength, and ductility. We will talk about another measure of ductility called percentage reduction in area before failure. You in fact measured it in your lab too. We are going to talk more why this is really a better measure of ductility little later. Then in lab number 4, next lab, we are going to talk about tensile toughness. And basically tensile toughness is the area under the curve. And a rough measure of this area under the curve is, if we imagine this to be a trapezoid, we can calculate this trapezoidal area, and this is what this approximation is. So let's talk about the lab 2 assignment that you just submitted and did on the two steel specimens that are here. So in lab 2, you were given two steel specimens, one coded blue, which was 1018 T4 steel, and the other one was 1018 T3 steel, which was marked yellow. So this T4, if you looked in the ASTM standard A109, you may have found out this was called skin rolled. That means during rolling, we applied small force so that only the skin or the surface became harder due to plastic deformation. Whereas in this T3, we applied a larger force so that it became quarter hard. If we apply still larger force, we can make it half hard. Even larger force, it'll become full hard, the highest hardness that we can get. So I had given you the basic tensile dimensions before and after failure, and also some key like load at yield and load at necking. And you calculated this yield strength, you calculated tensile strength, and then all of these properties. So you found out that as we increase the amount of plastic deformation, yield strength increases. So if we increase the amount of plastic deformation, which is also called cold work, so when we increase that, we increase yield strength. We also increase by 1.5 fold. We also found out that we increase the tensile strength. Not as much though. But on the other hand, we decrease ductility, both measures of ductility, elongation to failure, as well as percentage area reduction. So we decrease ductility. And this is what I mentioned in my big picture. This is what we see, that strength is inverse with ductility. Then I had asked you to compare it with published properties and to provide references. I'm quite disappointed that you complained quite a few of you complained about not being able to find references, even though I gave you at least the starting reference, which was A109, in which you could have easily found uh, the tensor strength, for instance, and ductility. In any case, I wanted you to just not only look at the published values. I thought many of you say that you are high achieving student and so on and so forth, but I did not find evidence of that. I wish you had read A109. You would have learned about cold rolling. You would have learned about cold working. You may have even found some other interesting properties that I'm going to mention a little later on. But in any case, these are not national secrets. These things you can find out if you invest time enough. But you need to read carefully, you need to invest time, and you have to be patient. You have to work like a detective. Uh, so anyway, let's talk about these properties. So elastic modulus E, you saw first of all that we had values like 27 and 25 against the published value of 30. It's almost 10 to 15% off. Now, it turns out that elastic modulus E for metals is a function of chemical composition only. So if you are not changing the chemical composition of the material, you cannot change the elastic modulus. It remains constant after any thermomechanical treatment. So that means if we begin with whatever condition the steel is, we anneal it, we skin roll it, we make it quarter hard, we don't change its elastic modulus. It should remain 30 million psi. In fact, when we go from iron, pure iron has same elastic modulus, 30 million psi. So when we look at this 1018 steel, so let's talk about this 1018 steel. What does 1018 mean? 1018 means the first two digits means this is plain carbon. That means carbon is the only alloying element in iron. And then this next two digits mean that the amount of carbon in the steel is 0.18%, and this is weight percent. We always talk about weight percent unless otherwise specified in material science. So this is a very tiny amount of carbon. So obviously when we go to this 1018 steel, we don't change its elastic modulus. It remains pretty much 30 million psi. So unless we add lots and lots of carbon and other alloying elements, we are not going to change the elastic modulus much. Now our measured elastic modulus was 27 and 25 for T4 and T3. We expected it to be about 30 MSI. This is pretty high difference. We expect the value to be within 3%. Now, in our case, the measured elastic modulus that I mentioned in this table, these two values, were measured automatically by the software. So if we look at this curve, the software just picked up 2 points here, drew a line, and calculated the slope. So obviously, if we were to do it manually, we can do better. We can choose 2 points which are on the line and so on and so forth. We can even get a better value by getting the numerical data and fitting a straight line, as some of you may have done, say, in your strength of materials course. I wonder if you remember how much the percent difference was. It is also possible that the extensometer was not properly calibrated. I don't believe so because I set the calibration to none long time ago, so I don't think anybody has messed up with the calibration. Possible they have. Another possibility is that the extensometer was not well aligned on the specimen. I did not conduct this test. This was done by Mr. Humphrey. Let's look at yield and tensile strength. Now, both strengths increase when a material is strengthened. We just spoke about this. Increase in yield strength is usually more than tensile strength. We saw that yield strength increased by if almost 50%, whereas tensile strength increased only about 10% or so. So we went from 31 to 48, whereas tensile, we went from 45 to 52. Now, our measured tensile strength should have been higher than the published values. So if you read your specifications carefully, these yield strength and tensile strength are typically minimum values unless otherwise specified. So the manufacturer says that these are the minimum values you can expect from our materials, and they publish this. So often, other than the ASTM standard, you should really be looking at where did you buy this material from and what were their material specs. That is what we really should be comparing to. Now, T4 has a strength ratio of 1.4, so that means it can be cold work considerably more than T3, which has a ratio nearer to 1. It still can be cold rolled more, as we know, because it is only quarter hard, so its strength ratio was 1.1 or so. Now, what about ductility? We found that ductility decreases when we increase the strength of a material. T4 had higher ductility than T3. That's what we expected. Both values are again higher than published values as expected. Again, in case of sheet steels, often again the manufacturer's ductility is minimum specified. And you found that both values were comparable to the published values in A109. Okay, the second part of the lab was I'd given you the Rockwell hardness 30T values along those tensile specimens, along these specimens where you see the dots. And basically what you did was you took the half lengths and then you plotted from left to right. So when you plot it left to right, first of all, you see that hardness is constant. It is constant in this grip area. And then as you start to deform, hardness begins to increase. So it increases. So first of all, we see that the blue specimen has lower hardness than yellow specimen, which we expect because it has lower strength. Blue has lower strength than yellow. Next thing we see is that both reach about the same maximum hardness. T3 has a slightly higher hardness than T4 because we see that their tensile strengths are comparable. The yield strength of blue is lower, so that's why the hardness is lower. And you can see that the slope of this curve, which tells us about its ability to cold work, in blue is higher than here, which is expressed by that strength ratio. So again, we see a higher slope. The hardness increases faster in blue than it does in yellow steel. So hardness increases as we get nearer to the fracture edge due to strain hardening in both specimen. Hardness is constant in the grip surface area because it has not deformed at all. And the slope of T4 is higher than T3, which is what we found from strength ratios. So another interesting thing I want to mention here is, again, going back to this A109, If you had read it carefully, maybe you would have found out that it mentions Rockwell hardness of these uh, sheets. You may have found out, for instance, some of you could have mentioned, was it a 15T hardness or was it a 30T hardness that was mentioned in that? And how do our values compare to what is mentioned in those specs? So those are the kind of things I expected you to learn on your own without my having to mention, go to so and so page and you're going to find value of 15 and please write 15 in your lab report. That would serve very little purpose. Okay, so let's talk about strain hardening, plastic deformation, cold working. These all mean about the same thing depending on the context. So let's see, we did tensile testing in which we took a specimen, we started stretching it, elastically deformed it, and then uniform plastic deformation began. And let's suppose we stopped at point D. We didn't let it go to maxima, we didn't let it fail, but instead we removed the load. So when we remove the load, it follows a unloading path that is parallel to this elastic deformation path. So we unload and we find out that at zero load, the material has experienced this much permanent deformation. So let's suppose we take the same tensile specimen and start stretching it again. So it's going to elastically deform all the way up to point D, because now that it has been strain hardened, its new yield strength is point D. And then it'll start plastically deforming again. So by giving it this much amount of permanent deformation, plastic deformation, we increased its strength. We strain hardened it. Or by cold working it by this much amount, we increase the strength. So you can see why we use these words interchangeably. And as we just noticed, that in this mechanical strengthening process, we do not change elastic modulus. We do increase, depending on the material, yield strength greatly. We increase the tensile strength somewhat, and we reduce ductility greatly. You are going to learn, hopefully in a few weeks, that during this plastic deformation process, dislocations move and multiply. The dislocation density, if we go from, say, yield strength to tensile strength, increases by factor of 100 to 1,000. Now, I just don't have the time or really focus on this, but if you want to learn more about cold working, read chapter 8 of your textbook. There are various ways in which we can cold work a material. One of the ways is rolling. We just spoke about it. Basically, what we do is we take a thicker sheet and pass it through the roll so it decreases its thickness, just like as is shown schematically here. So what we are doing is we are reducing the cross-sectional area as we go through each rolling pass. Another way we can do it is we can compress it, cold deform it, do a cold forging or a die forging. We can also do extrusion, push the material through a die as in extrusion. So for instance, I'm going to talk about cold work steel. I'm going to use the word cold rolled. It is not really rolled, it is extruded. So these are specimens cut from extruded rods. We are going to use this for our demo. And then you are going to work with these brass samples, which are really rolled. So I have 3 levels of rolling, cold rolling. So they have 3 levels of hardness that you are going to measure. So here is, for example, cold working of low carbon steel. So these are the results from cold rolling or cold extrusion, where you start with a large area and you reduce the area by extrusion or rolling. So we define our percent cold work by this percent reduction in area. So now you can see why I mentioned that ductility expressed in form of percentage reduction in area is a better measure. So we have this low carbon steel. If it is in annealed state, that means 0% cold work, we see a very interesting phenomena called yield point phenomena. So I hope your professor in your lecture course would talk about it. This is the role carbon plays in iron. So in any case, you can see its yield strength is low. We give it a 4% cold work, we increase the yield strength from about 250 to nearly about 400. We go from 4% to 24%. We increase the yield strength from about less than 400 to about 500. So you can see by the process of cold working, cold rolling, cold extrusion, cold forging, we can make a material stronger. But the price we pay, you can see right away, is in ductility. 0% cold work has high ductility. This blue one, which is 4% cold work, lower ductility, and the red one has the lowest ductility of them all. Okay, so let's look again at what we are going to do in this lab. We just finished talking about effect of cold rolling on tensile properties of the mild steel and other materials, of course. But my example was from mild steel. Now, what we are going to learn today is about Rockwell hardness testing. This is one of the most common hardness testing technique that is used in many, many different ways. It has got many different scales. We are going to focus in my demo on 3 different cold rolled steels. So I have 3 different steel samples which have different hardnesses. I'm going to make a Rockwell C indentation on them. And then we are going to measure the size of these indents using Fiji. We are going to talk about different ideas in hardness. And I hope you have downloaded this ASTM standard E18, and I hope you become really very familiar with it. And then, as usual, you are going to critically evaluate numerical results and make summary conclusions on your specimen. So for your specimen, what I'm going to do is I'm going to give you 3 different cold rolled brass samples. I'm going to make Rockwell B indentations on them. And then you're going to measure their size and do things similar to what I'm going to show you in my demo. And the lab report is due Wednesday, March 3rd. Okay, so let's talk about hardness testing. What is hardness? Hardness, as you know, is resistance to localized plastic deformation at surface. So this is what we meant by indentation hardness. When we did Brinell hardness testing, we applied a force on the indenter and caused that indent. Now it turns out hardness is not an intrinsic material property. You saw that it does not appear anywhere on our tensile testing curve. In fact, it is a function of 3 of those tensile testing properties: elastic modulus, yield strength, and what we call strain hardening behavior. Quantitatively, we characterized as that strength ratio of tensile strength to yield strength. So we are going to talk about this a little more in a minute. But it is also very dependent on surface conditions and porosity. So whether the surface is rough or smooth, it can change the hardness. Whether the surface is less or more porous, it can change the hardness. It's also dependent on test instrument geometry and how we measure it. The key thing is it's commonly used in industry for process or quality control. As you have seen that it is a very quick, very inexpensive process. So often when a material is undergoing process, going through some thermo or mechanical process, we pass samples along so that we can monitor their hardness and see whether they have gone through the right process or not. So it is used for grading similar materials. So you do not want to compare aluminum to steel other than in a qualitative way that we know aluminum is softer than steel. That is about all the comparison you want to do. It is used for monitoring uniformity of a treatment such as forming, alloying, heat treatment, case hardening. Hopefully some of these words would make more sense to you as you go more into your course, more like eighth or ninth week. Uh, since it has such a great correlation with other properties such as tensile strength, wear resistance, which are more time or consuming or expensive to determine, we use hardness tests a lot. Even though we are going to talk essentially about indentation hardness test, I want you to be aware that there are other kind of hardness tests. So for instance, in mineralogy, they use a scratch test, which has its own scale of hardness called Mohs scale of hardness. In case hardened materials, uh, for portable and non-destructive use, there is a rebound test called the Lieb test. Then for rubber-like materials, there is a pin penetration test, and that tester is called a durometer. Um, so that is used for testing hardness of rubbers. And then finally, we have the indentation hardness test, which is what we use very commonly for metals, and even it is used in plastics. Indentation hardness test is common because it is very quick, easy, and inexpensive. And there is a variety of load ranges and indentation sizes. We cannot compare really hardness number from different tests. So we cannot compare Rockwell C to Rockwell B or Brinell to Rockwell and so on and so forth. There are ASTM standards for each of these tests. For Rockwell hardness test this week, become familiar with E18 in lab 1. Hopefully you became familiar with E10. In a later lab, you will become familiar with Vickers hardness called E92. Almost all of these equipment look something like this. Basically, they have some way of applying a force. There is an indenter. You place your specimen on this anvil, and there is some kind of a LED, LCD display in most of the modern instruments. So we already did Brinell hardness test in lab 1. In this lab, I'm going to talk about Rockwell hardness test on regular thick specimens. So you can see these are thick specimens. Even though in lab 2, you remember we did the 30T and 15T tests. Those were on thin specimens. Um, I had it on my table a few minutes ago. Then in a later lab, we are going to talk about micro indentation hardness test. And there are two scales there because they have two different indenters called Knoop hardness and Vickers hardness. Before I go on, in any case, whatever you do, you want to make sure that both the bottom and top surfaces should be clean because the dirt on the surface could shift. Now, you have been asking about questions on my quizzes. Obviously, when you apply a certain load, whether it is 3000 kgs or in our case, 150 kgs in C scale that we are going to apply today, the indentation size does not change. So in Brinell, since we measured the indentation size, our hardness number would not change even if the specimen was dirty or there was some tiny particles acting as springs at the bottom. But in Rockwell hardness, as we are going to talk about again, it is the machine that measures the depth of indentation. So the machine thinks it has gone deeper into the material than it has, and therefore to the machine it appears that the material is softer than it is. Of course, do not measure near an existing indent because the area around an existing indent is strain hardened. Do not measure near an edge because the edge does not provide any support. So the material is going to appear softer. And always identify the hardness scale with the number and applied load when it is appropriate. So for T scales, you remember you have to say whether it was 15 kg, 30 kg, or 45 kg. But for C scale, you will find out soon that the load is constant, so you don't need to specify it. So Rockwell hardness test is useful for both soft and very hard materials. So obviously you are going to choose a different scale. For thick specimen, the most common scale for metallic materials, B scale for soft or non-ferrous alloys. Non-ferrous means where iron is not the predominant element, such as aluminum, brass, copper. We use B scale. C scale is used for steel and harder alloys. So we are going to use C scale for our demo samples. C scale for demo samples, and you're going to apply B scale for your brass sample. Now, there are also what is called superficial Rockwell hardness test for thin specimens. In case of metals, instead of B scale, we use T scale. For soft non-ferrous alloys, we use the same indenter as that we use for B scale. And then we use N scale for steel and harder alloys. We use the same indenter as for C scale. So this is what the indenters look like. So this is our C scale indenter. It's a diamond cone at the end, very end. And B scale, we have a 1/16 inch tungsten carbide ball. There are, of course, other scales for special purposes. So plastics have their own scale with their own different indenters. So if we look at Rockwell hardness B scale, we have this 1/16 inch tungsten carbide ball indenter is the standard indenter now, tungsten carbide instead of hardened steel. So often when you see this W at the end, it means that it is following the new standard, tungsten carbide. If it was the old standard hardened steel, you would not see this W after that. So what we do is we apply a minor load first. I'm going to show you a video in a few minutes. In case of B and C scales, the minor load is 10 kg. So it is used to seat the indenter and establish the reference for depth of indentation measurement. And then the major load we apply is 100 kg. And the machine measures the depth of indentation in microns. So it uses this formula 130 minus h over 2 mu. So we can find out therefore the hardness of the indent. I'm sorry, the depth of the indent if we know the hardness and vice versa. So you can see that as h increases, so as h increases, this portion is going to increase. So we are going to be subtracting a larger number from 130. So our RB is going to decrease. So the deeper the indenter goes into the material, the softer it is, or the lower the hardness number. So we identify as 42 HRBW. The number might be written before or after. In Rockwell hardness C scale, what we do is we use this conical 120 degrees synthetic diamond indenter. So our indenter is shaped like this. And this angle is 120 degrees. And this is our depth of indentation. Again, H is in microns. Same minor load, 10 kg. But this time the major load is 150 kg. And we use the formula again, 100 minus H. H is in microns over 2. So again, you can see as H increases, our hardness is going to decrease. Again, many ways of writing this, but basically we are identifying it is Rockwell and C scale. Everything else becomes fixed. Good afternoon, folks. This is our Rockwell hardness tester. It is a Clark model CR3E. This allows us to do both regular Rockwell hardness testing as well as superficial Rockwell hardness testing. I'm going to switch on the machine, which is at the back. It takes about 20 seconds to initialize. We have a load dial here where we can go loads from 15 kgs to 150 kg. On the top we have a band, just like in Brinell hardness testing. I was raising the anvil to seat the indenter. Same way I'm going to raise the anvil to apply the minor load. Once the minor load is applied and this LED shows me this green set button, the machine takes over, applies the load, dwells on it, and unloads it and displays the hardness reading right away. No measurement needs to be made. The machine makes the measurement of the depth of penetration after the load has been removed. So here on this panel, we can select on this LED panel what hardness we want. So we can change it. Right now it is set for hardness Rockwell B. We have the indenter, a 1/16 inch ball indenter mounted here. We change the minor load application through a dial here, which is set now for R. R means regular Rockwell test. In the next video, when we do superficial hardness testing, we will see how we can change this minor load. So for Rockwell B, we need 10 kg minor load, we need a ball indenter, and we need 100 kg here. If my load setting was not proper or not appropriate, it would select the appropriate scale. So right now 100 kg is the correct scale for HRB. So now we are ready to measure our hardness. So here is the sample we are going to measure our hardness on. So we place the sample underneath the indenter. I'm going to raise the anvil, and if you watch this band, when the load reaches 10 kgs, the machine takes over. So the machine has now taken over. It reset it to 130, which is the baseline. Applying the load now. It has removed the load, and now the hardness reading is displayed to 46.6. I'm going to remove the load by lowering the anvil, and we can see that we have made this indent right here. Okay, we are going to be working on steel, so we are going to be using C scale, which has a conical diamond indenter. So let's look again what we are going to do in this demo. We are going to do Rockwell hardness testing. I have got 3 specimens here. These are really extruded, but I keep calling them cold rolled because that's typically the terminology sometimes used. They have three different hardnesses. So the specs are 30.3 plus minus 1, 43 plus minus 1, and 61.9 plus minus 1. Again, hardness, Rockwell C scale. So once I have made indentations, I'm going to measure the size of indents with Fiji. We are going to calculate the apparent depth of indentation. We are going to calculate another thing called a Meyer hardness number. We are going to analyze the data, evaluate the results, and make summary conclusions. So I would like you to create an Excel template. I have posted it. It is going to be nearly identical to the one you're going to use for your assignment. I've just changed probably just a few words like hardness, Rockwell, BW, and your material, etc. So let me fire up my template. So Lab3 demo template. So here is my template. I am going to size it up. And here it is. So I have made indentations, 6 indentations, hardness Rockwell C on this specimen, which is marked HRC 303. So you will see I've labeled images with the hardness there. So let me fire up Fiji now. See, Fiji is here. And I'm going to open the file. Details. Okay, so I want hardness Rockwell 303. So these are my 6 indents. And first thing I'm going to do is analyze set scale. So I have taken this, it's a 8-bit image. I used a 9600 DPI scanner. So the distance pixels 9600 is 1 inch, we know, but I don't want to use 1 inch. Remember, our 1 inch equals to 25.4 millimeters, which is 25,400 microns. And that is what we want to measure in microns. Okay, then next step, we are going to set our measurement. We want area, we want perimeter, We want add to the overlay. We want to display the label. We want results in scientific notations, and we want 4 decimal places in our scientific notation. Then what you do is you start magnifying your first indent. So this is our magnifier tool. You have done this before. And try to magnify as much as you can. I always have this problem grabbing the whatever your screen will allow without pixelating. And then use the ellipse tool. Fit your ellipse. Okay. So do as good a job as you can. And then Control M. And it has labeled it area, perimeter, measured it. Then you use this hand and you can scroll through and get to your next indent. And then you measure your next indent, Control M, measure next indent, Control M, and you would have 6 measurements. And then what you do is you file, save as, TIFF file your image, which has got the labels and your fitted ellipse. And you can also come here and file, save as, and you can file this, your measurements, as a .csv file. Okay. Okay, folks. So I have one file, the table of my measurements on this HRC 303. I also have a corresponding image file that I have saved. I'm going to transfer these values to Excel sheets. But before I do that, I have repeated these steps for my other 2 specimens. And these are uh, labeled HRB 430 and HRB 619. Okay, so here is my spreadsheet. And I know several of you have complained that I give you PDF, but not the Excel spreadsheet, which would make your life convenient. But I really want you, by typing it in, to appreciate, first of all, the structure and also how I try to highlight things and also use these symbols. So I do want you using appropriate symbols, etc. Okay, so let's open up our first file for 303. So this is our Excel file. This is the comma separated file that Fiji has created. So what I'm going to do is I am going to copy all of this into my template. So this is the point I'm trying to make. I have to structure it so that I made it very easy for you to copy. Now let's go into file HRB 430. And I'm going to take all of this, copy, and paste it. Right, let's go to the last one, 619. I'm going to take all of this, copy. Oops, I had not pasted it. What did I do? Wrong one. Okay, and then go to 619. Okay, so I have my data. Let me close all my remaining files. So we need to calculate the depth. So let's talk about depth. So we have a conical indenter. This angle is 120 degrees. So this angle is 60 degrees. So if h is our depth, then this is diameter of the indentation by 2. So we know diameter over 2 over h is tangent of 60 degrees. So our h would be therefore d over 2 times tangent of 60 degrees. Now, when you are going to be doing your demo, you have a 1/16 inch diameter ball. So what you would need to do is you would need to fit a circle to it of this diameter so that you can relate your depth of indentation to d over 2 for your Rockwell B scale. Remember, mine was C scale, so I used a diamond indent. So let's type this formula in. Now, we are going to get our D from our perimeter measurement. So remember, our perimeter measurement is, let's say, P, and we get what is we called Ferret diameter, right? So this was our Ferret diameter. In lab 1, we found that it gave us the best results. So our formula is going to be perimeter divided by pi, that gives our diameter, divided by 2, divided by tan of 60 degrees, but Excel works in radians. So that's our diameter. And we copy this formula all the way down. Okay, now we need the Rockwell hardness that we had measured. So remember, when I made the indent, the machine gave me Rockwell C values. So I've got that in a file somewhere. Okay, I have got my hardness data in this Excel file. So again, I was intending to provide you a PDF of this hardness data. But this time I'll be kind to you for your assignment, and I will give you the Excel file. So I'm going to copy this data. These are my indents, and I'm going to paste it in my template file. Okay, so we are good. Let me remove some of these things. So we have done the measurements and we have done the Excel data transfer. So we are ready for some analysis. So before we do some analysis, our depth, we want to display in numbers. So we want to display 1 digit because we can measure it as good as about, let's see, 9600 dpi is equal to 25400 divided by this 9600 dpi, and we have 2.65 microns, 2.7 microns. So that's about our precision. So I always tack another digit just so that we know how we are going to round it. Okay, so let's plot depth versus Rockwell. Insert XY scatter. Let's move this chart to new sheet. We are going to name it depth. Okay. Oh, by the way, since I want you to submit those Excel sheets, you might want to add them as sheets. So remember, we opened HR 303. So you might want to take all of this, copy first to your spreadsheet, like a new sheet, and name it HRC 303. So you should have your main sheet is data. You should have three of these Fiji measurements. And then now we are creating this plot. Okay, so we have this plot. Let's try to first um, adjust our axes. So we see our numbers are like from 120 to about 250. So let's start with 120. You can even make it 100, doesn't matter. 140 was pretty good. Okay. Then it has got too many decimal digits. So let's display the fewest needed. So that'll be 0. Okay. Same thing on the y-axis. So most of our numbers go from something like about 25 to about 65. And again, we have extra decimal digit. Okay. So that's good. Then what we want to do is we want to fit a straight line. So we select all our data and we say add trend line. So we want to fit a straight line, linear, and we want to display the equation, display R square. So it displays all this, and let's move this to kind of top of the chart or something. That's our line fit. So you can see that it is 117 minus 0.38x. Downward slope as we expect. What do we expect? As hardness increases, depth of indentation should go down. So that's good. Okay, let's put up some titles, etc. So we start with always chart title above chart. So this is Rockwell hardness versus indentation depth. Okay, x-axis, indentation depth in microns. Okay, vertical, Rockwell hardness. This is HRC. Okay, pretty good. Now, ideally, would like to transfer this information into the spreadsheet. Unfortunately, charts are graphic objects, so we can't transfer information easily. But what we can do is we can use line fitting function that is within Excel. So it is very simple. If you want intercept, you type intercept and then you select Y values first. Y values were our Rockwell C, comma X values, which was depth, enter. So that was our intercept. For slope, type slope, Y values, comma X values, enter. R square, RSQ, Y values, comma X values. So let's adjust this. We want no more than one digit there, 3 digits, 2 digits. Okay, so this is a pretty good line fit. Oops, these values are for belong here, depth curve. Okay, sorry about that. Okay, Meyer hardness. What is Meyer's hardness? So let's look at Meyer's hardness. So in research, we want a very common hardness number. So Meyer's hardness is often used in research, and it's a very simple idea. It says load in kg divided by area of the indentation, whatever shape. And this is in millimeter square. So our units are kg per millimeter square of our Meyer hardness number, but is usually just stated as a number. Oh, it is kg times g, so it is in Newton times g. So it's in Newton per millimeter square. Okay, so to get Meyer's hardness number, what we are going to do, we know our load is 150 kgs. In your case, it is going to be 100 kg, remember, for B, times 9.81 divided by area of indentation. So this area of indentation is in a micron square. So what we are going to do, we are going to multiply it by a million to get millimeter square. Take this, copy it down. Okay, let's adjust number of digits. So we are going to display 0 digits, number. Okay, so now we want to plot Rockwell and Myers hardness. So insert chart, move it. This is our Myers hardness. Okay, let's do the same thing, adjust x-axis. So our values look like between 25 to 65. Okay, y-axis. Oh, let's adjust, we have extra digit here, so let's do that. 0. Myers hardness goes from about, looks like 2,500 to about 8,000. So let's make it 2,000 to about 8,000. Selects it. Don't need to format anything. Let's fit a straight line. Okay, display equation r square. So let's move this so it is visible. Okay, let's do chart title. So we have Meyer hardness versus Rockwell hardness. Okay, x-axis Rockwell hardness HRC. Y-axis Meyer hardness number Newton per millimeter square. Okay, there we are. So now we want to have this line fit and r square using the Excel functions. So we are going to type intercept y values, comma, x values. Slope. Okay, and r square. Here we are. Let's adjust this whole number. Let's adjust this to a digit. Let's adjust this to 2 digits. And that's it, folks. That's our spreadsheet work. Okay, so let's discuss these things. So we did Rockwell hardness versus indentation depth. I defined Meyer hardness number. Here is the formula. So we have a diameter measurement resolution about 3 microns. Okay, and notice our diameters we can calculate using this perimeter value, and you can find the precision. So the precision is very good, less than 1%. Now the averaged measured values in HRC 303, so I averaged these values, was 30.8. It's within the range. For the next sample, 44 is in the range, except that notice 2 indents are out of spec. Average is okay, but 2 indents is out of spec. 61.9, our average value is 61.8. All of those indentations are in spec. And of course, we found that hardness of 303 was small, least cold rolled, cold worked, middle cold worked, most cold worked. So we expected. Now we found experimentally that our HRC values measured by the machine, H measured or calculated through Fiji, was this formula. Remember, our scale, our C scale is based on the H measured by the machine. So we are kind of there. We have 117 instead of 100, 0.38 instead of 0.5. Line correlation is very high. If we had many more measurements in all kinds of different ranges, we might have come closer to this. Now, for Meyer's hardness number, we got this formula. Of course, ideally, what we expect is we expect it to be linear, right? And it is. Line correlation is pretty good, 0.95. Let's see if you make some other observations on your own. You have the demo data from me, and of course, you'll have to make comparable observations for your assignment sample. So for your assignment, what we are going to do is I am going to give you 3 brass samples. So I have these 3 brass samples. And let me see what their hardnesses are. So one has a hardness of 37.0 plus minus 2.5. Remember, these are hardness, Rockwell. B with tungsten ball. So this file is named HRB 370. This is 50.5 plus minus 2.5. So this file name is HRB 505, of course. And our last sample has a Rockwell hardness of 74.8 plus minus 2.5. This file is named HRB 748. And then, since I made hardness indents on these, I will give you an Excel file that contains these hardness Rockwell values. Okay, folks, I hope you enjoy the lab.